Hi everyone. Today we are talking about pulleys. We are going to make pulleys real in our physics now. They've been massless up until this point, so now we are going to use some real pulleys. So a pulley of radius r and mass m and moment of inertia I is mounted on a frictionless axle. A light cord, so you can't get away from massless, right? So a massless cord, light cord supports a hanging mass of lowercase m. Calculate the linear acceleration, rotational acceleration, and tension in the cord. So this is one of those problems that tells you to calculate three things, but you're going to have to calculate one to get the other two. So tension, we're going to calculate indirectly because that's going to be required for our math. But as we go, we'll work through that. So first, what we want to do is we want to establish a couple things first. I do want to say that we've got the summation of force equals mass times acceleration. I want to say that acceleration equals alpha r. I also want that this summation of torque equals I alpha, and that I equals the summation of mr squared. All of those are going to be able to be discussed as we do this math. So first, the linear acceleration. Linear acceleration, when we do summation of torque, is relatively simple because we can do it very similarly to how we did summation of force. We're actually going to do summation of force. We're going to tweak torque a little bit to make it force. So first, let's look at the small mass m. We see that there's mg down and tension up. Okay, we see that there. They've already got the diagram for us. However, since the direction of motion is downward for the block, and as that pulley goes around, it is going counterclockwise, which would be positive, so we'll call counterclockwise positive, making down also positive. So for little mass, okay, we've got m1g minus the tension equals m1a. Okay. Now, to solve for the linear acceleration, we could just divide by little m. I guess that's not m1, that's little m. And we'd be done. But you don't want tension in your problem, in your answer. Tension, like I've said many times, you can get rid of it if you do your math right. So let's go ahead and get rid of it. That's the equation for little mass. Let's look at the equation for big mass. Okay, we've got the summation of torque equals I alpha. Now the summation of torque here, okay, that is tension crossed with the radius, which equals I alpha. Now we also know that this pulley is a solid disc. Okay. Solid disc or cylinder, okay, that has a moment of inertia of mr squared over 2. So we'll go ahead and put that directly in here. You've got mr squared over 2 alpha. Okay. Now, we don't want torque here, right? We're trying to solve for tension in terms of acceleration. T in terms of A. We don't want alpha, and we don't want to have this radius sticking around. So let's divide by radius across the board. So now we've got tension equals mr squared over 2 alpha divided by r. Now I'm not going to get rid of that r quite yet because we're not done dividing. Because like I've said earlier, up here a equals alpha r. So if we're going to substitute out that alpha to substitute back in here, if we put in an alpha over here and we've got an a in the same equation, that's just going to cause headaches. Then you can't solve for one because you've got the other. So what we're going to do is we're going to say that alpha is, up here you can see that alpha is a divided by r. So that means that this is mr squared divided by 2a divided by r squared, right? We're putting in an a divided by r. So now both of those r's cancel. And now we have the fact that tension equals m over 2a. Now we're going to put that back over here. Okay, that is our tension, and our tension goes right there. So we now have little mg minus big M A over 2 equals little m A. Now we're going to get the a's on both sides, isolate. So you've got little mg equals a times, so that's little m plus big M over 2. And now to divide that over, mg divided by m plus big M over 2 equals a. That is our linear acceleration, right? Now, that is, let's see, let's look at what we're asked. It's linear acceleration, check. Tension, like I said, solved for in the green down there because we had to solve the problem. Physics problems do that all the time. They ask you for several things, but you've got to solve for some of it to get your problem solved anyway. Now let's get our rotational acceleration. If A equals alpha r, what we're going to do is we're going to take alpha in A divided by r. So let's take our A, mg divided by little m plus big M divided by 2, and we're going to divide that by our radius. Okay? And this is our rotational acceleration. So that gives us, little m. My penmanship doesn't really give a whole lot of hint to what is a little m and a big M, but I'm trying. Okay, so this is our angular acceleration, right? We've got mg over r times m plus M over 2. However, it is customary to try and show your alpha in terms of torque and moment of inertia, because torque is I alpha. Okay? Again, one of the equations we've got up here. Now, if we want I alpha, okay, or I'm sorry, if we want torque divided by I, divided by moment of inertia, what we're going to do is we're going to multiply this by R over R. Okay? Just multiply by 1. But that changes its form. Now, instead of mg, you've got mgr. And remember, torque is force times radius. Now you have a force times a radius. Now we also have m plus big M over 2 times r squared. If I, remember, last equation that I'm going to use here, okay, I is the summation of mass over r squared. Here you've got the summation of some mass times r squared. So this is your alpha, which is going to mean that the system's torque is mgr. Notice that mg is serving as your net force, and the moment of inertia of the system, I guess, would be m plus big mass over 2 times r squared. So that is how you want to solve for your alpha. Okay? You want to get that in terms of torque over moment of inertia, because if you just stick with this, okay, if you stick with this and you try to use that in terms of torque and moment of inertia, it kind of falls apart because this isn't in the correct format. So we have in blue our alpha, in black our acceleration, and in green our tension. So that's how we were able to solve that problem. Now we have two real pulleys. Two blocks of M1 and M2 are connected by a light cord that passes over two identical frictionless pulleys on the ends of a table with moment of inertia I and radius R. Letter A just says draw the scenario. Let's make sure we understand what's going on, right? So we have two pulleys on the ends of a table. Okay. I'm going to say this is pulleys P and Q. Now then we have a string going over the pulleys that connects mass 1 and connects mass 2. Okay. So that is the situation we're dealing with. Now I also want to clarify that these tensions are also going to be really important. The next question will emphasize that. So we're going to say that this is tension A, tension B, and tension C, just because I number things left to right. So that's the situation we're dealing with, right? And then we obviously have M1G and M2G involved as well. Now, letter B says, if the blocks fall in mass one direction, right? They are falling this way. Okay, that is your direction of motion. If they are falling in that direction, rank the tension in the ropes conceptually. So this is kind of hard to do without any numbers, right? But then you can think, what is each tension responsible for moving, right? So if we look at tension C, okay, over here on the right, this is responsible for moving M2. Okay, now if we look at tension B, this is responsible for moving M2. But now we're using real pulleys. So it is also responsible for moving the mass of pulley Q. Then if you look at tension A is pulling M2 and the mass of pulley Q and the mass of pulley P. And M1 is then making all of this happen, right? So now we can see that tension A will be greater than tension B, will be greater than tension C. And we can see that conceptually just by seeing what are they responsible for moving. Now, if we want to derive an expression for the acceleration of the blocks in terms of M1, M2, G, I, and R. So we're not going to use the mass of the pulley Q or mass of pulley P. We're using I and R. And I'll show you how we're going to do this. So to do this, we're going to use stack and rack. This is a method that we used way back when we were doing Summation of Forces. I think that's chapters 3 and 4. So it's a very similar method. Okay, so let's look at the free body diagram for M1, right? M1, you've got M1G down, and you've got tension A up. For M2, okay, you've got M2G down and tension C pulling up. But you also have to look that the direction of motion is going to determine what is positive. So the direction of motion for M1 is down, but the direction of motion for M2 is up. And then the direction of motion for TB will be to the left. So that shows the motion of all of this. That also shows the motion of the acceleration, okay? The acceleration may change its direction along the path, but that means that that direction of motion is what's going to define our positive. And you've got to stay consistent on that. So for M1, let's see, do I have room down here? I do. So we've got M1, okay, its summation of forces are going to be M1G for the positive and tension A for the negative, and that will equal M1A. For M2, TC will be positive, and M2G will be our negative, and that yields M2A. Now, what makes this different from everything we've done before is that we're now considering the pulleys. So let's consider pulley P. Okay? Pulley P has a summation of torque, not necessarily a summation of force, but we can make this a summation of force. Remember, summation of torque equals force crossed with radius. So if we divide summation of torque by radius, we can actually get summation of force. Okay? So we've now got P over R. Okay? This is really the mass of the pulley divided by radius, right? So if we're keeping the same verbiage that we were using for M1 and M2. Now, the summation of torque is now the summation of force. Okay? So for pulley P, okay, we see that tension A is pulling it forward. Tension B kind of represents the resistance of Q and M2. So here we will have TA minus TB equals I alpha over R. Now, what is not convenient, right, is that A equals alpha times R, not alpha divided by R. So we can't say, oh, alpha divided by R, that's A. It's not. So to get this in terms of acceleration, because remember, that is the whole reason we're doing this, we need to substitute this out. So alpha divided by radius is I'm sorry. A divided by R is alpha. Okay, so if we're substituting in for alpha, you've got to put A over R. So that means we have IA divided by R squared. And I also want to note that I is the summation of mass times R squared. If you divide I by R squared, you're basically getting the summation of mass. So if this is a summation of force right here, if that's summation of force, this is essentially MA, all by dividing and manipulating. Divide by R and then manipulate your alpha to become linear A. So now this can go right back into our stack and rack. We've got MP over R. Okay, that is represented by TA minus TB equals IA over R squared, or I over R squared times A. I'm going to couple I over R squared like that because they kind of represent the mass in itself. Right? Now for Q. Okay. For MQ, we've got, let's look at our graph or our picture. Q is being pulled forward by B and resisted by C. So you've got TB minus TC, and that will equal I alpha divided by R, right? We're just assuming that we've already divided our summation of torque by radius. So this will again yield IA over R squared. The reason we're not making a big fuss about this is because the moment of inertia and radius are identical. Okay, we've got two identical pulleys. So that's why the MQ and MP doesn't have a different IP or IQ or RP and RQ. So that also equals IA over R squared. So we will put that right over here. That fits MQ over R. You've got TB minus TC equals I over R squared A. Now what we're going to do is stack and rack. You essentially add everything up. However, tension A, you've got positive and negative. Tension C, positive and negative. Tension B, positive and negative. Remember, tension can usually be canceled out or substituted away if you do your math right. So all we are left with is M1G minus M2G, and that will equal, I'm going to factor out the A in all of that. So you've got M1 plus M2 plus 2 I over R squared. Okay. So what you do is you essentially add all of these up, right? You've got M1A, M2A, I over R squared A, I over R squared A. I just factored out the A in all of that. Now to get your linear acceleration, you're going to divide M1G minus M2G divided by M1 plus M2 plus 2I over R squared. And that all equals your linear acceleration of this system, of this pulley system. So that's how you're able to do that. Stack and rack is going to be your friend when we start using summation of torque and summation of forces in the same problems. Now, as you could see before, a real pulley does affect tensions, right? Tension A was greater than tension B, which was greater than tension C. If those pulleys were massless, that's a whole different conversation for chapters 3 and 4. But for chapter 10, we're using real pulleys. So in this system, we have M1 equals 2 kilograms, M2 equals 6 kilograms, big M, mass of the pulley, equals 10 kilograms, radius of the pulley is 25 centimeters, and the incline is 30 degrees. coefficient of friction for both blocks is 0.36. The pulley can be modeled as a solid disk. So this just gave us all of our givens. M1, 2 kilograms. M2, 6 kilograms. Mass of the pulley, 10 kilograms. Radius of the pulley, 25 centimeters. Theta, 30 degrees. Zoom in. You got mu k, 0.36. And it told us the moment of inertia without directly telling us by saying it can be modeled as a solid disk. Solid disk would be mr squared over 2. So now that we have all of those givens, we need to find the linear acceleration of the blocks. Now we're going to do basically the same method, but now we actually have numbers. So this is going to get more complicated. We also have an incline, so that is going to get more complicated. But let's look at our free body diagrams first for M1 and M2. Okay, so M1, you've got M1G, you got normal. This way, let's label our tensions A and B. I go left to right, so you've got tension A and tension B. So this would be tension A, then resisting us is friction. Right? Now for M2, this guy is on an incline. So we have M2G with a vertical and a horizontal component, right? Determined by theta. Now, it's got a normal force. And backwards, it has 2 forces. That would be tension B and the friction force. I'll call that friction 1 and friction 2, just to keep those separate. We get that right? Yeah. Gravity's pulling it down. Normal, B, got it. Okay. Now, we need the linear acceleration of the blocks. We'll start there. So let's get our summation of forces for these. For M1, okay, we're just dealing in the direction of motion, right? So in the Y, we're going to disregard those kind of. Friction is going to make us remember them, but we're going to disregard them for a second. We've got TA minus the friction force equals M1A, right? And remember, since it's all connected by one continuous string, assuming the string doesn't slip on the pulley, then this string will be taut the entire way. There's no slack. The string doesn't break. That means the acceleration is the same for all parties. Now, I'm going to get rid of that friction, okay? Because that's not real proper. You've got mu k times normal. Normal for M1 is M1G. So you've got mu k times M1G. So I'm going to put that in for our friction. So you've got tension A minus mu k M1G equals M1A. And that's going to be the start of our stack and rack. Now for M2. Okay, M2, a little bit more complicated. We've got M2, we've got our positive force. Now remember, positive follows direction of motion. We are assuming that's your direction of motion, and then we assume that this is your direction of motion, right? Ooh, sloppy arrow. Surely that sitting block M1 is not pulling the other block up the ramp. It also tells us that they've got friction. We assume that they're moving due to that. So you've got, what's pulling you down is the horizontal component of gravity, right? So that would be sine theta. So you've got M2G sine theta minus the tension in B minus the friction force. But let's substitute out for that friction force. You've got mu k normal. Let's substitute that normal. Normal is mirrored by the vertical component of M2G. So that would be cosine, right? So you've got M2G cosine theta, right? Cosine because it is adjacent, sine for the horizontal component or the x component because it's at the opposite end. And that all equals m2a. Okay, now that's ready to put over in our stack and rack. So we've got m2, m2g sine theta minus tb minus mu k m2g cosine theta. That equals m2a. I really should have just copy pasted that over. I can do that. I forget that I can do that sometimes. Now we have the pulley, right? Let's look at that pulley. For the pulley, the summation of torque, right? Summation of torque will be I alpha, but remember we will divide all of that by R. So we've got M over R is our forces. What's pulling it is the tension B. It is resisted by tension A, and that all equals I alpha divided by R. Now remember, if we want this in terms of A, we will have to use our bridge equation. So A divided by R is the alpha that we're substituting in. So that becomes I over R squared A. Remember, I over R squared kind of represents a mass. So we will take that and move that on over here. You've got M over R. That represents TB minus, TA. And that equals I over R squared times A. And again, we just stack and rack. So add these guys up, positive and negative TA, positive and negative TB, but the rest is going to stick around. The only positive we have left is M2G sine theta, which makes sense because that would be the only force driving this motion, right? Is the gravity pulling down M2, then the friction is the only thing opposing it, because the tensions are just connecting everybody. Tensions go away. So now we're going to include our tension, or our friction. You've got mu k m1g minus mu k m2g cosine theta. Okay, and then we need to add up all of our a's. Okay, so you've got acceleration times m1 plus m2 plus I over R squared. All right. Now we can divide all of that over. Divide, copy, bingo. Now we're done. Or are we? Because now we have givens. Okay. So now all of this has a value. So I'm going to write a little bit bigger so that I can, oh, can I fit all this? I've got room. So M2 is 6, G 9.81, sine of theta, which is 30, minus mu, which is 0.36, M1 is 2, G 9.81, minus 0.36, times, what is our M2? M2 is 6, times 9.81, cosine of 30. That's in our top. Now before I do the bottom, I do want to look at the I divided by R squared. Okay, our solid disk, right, is represented by mr squared over 2 divided by R squared. So we can simplify this to say that is m over 2, and we have m, right? M is 10. So when I get to I over R squared, I'm going to put in 5. Right, yeah. So M1 is 2, M2 is 6, then M over 2, or sorry, yeah, M over 10 divided by 2 is 5. Now that acceleration put that in our calculator. All right, so when we put that in our calculator, I got 0.309. 0.309. Now, if we look at our units, right, we're using kilograms, meters, degrees, unitless for the coefficient of friction. So this is all SI units, so that should remain meters per second squared. So that's how we can find the linear acceleration of a system of blocks and pulleys in a real pulley world. Now, we didn't include any friction in the pulley, but that would just be taken into account in your summation of torque. Then in here, you would just have minus friction for your pulley, right? So if we do have a frictioned pulley, not a frictionless pulley, that's how you would include that. Now, the tension in the string on both sides of the pulley, which is not equal, okay? So if we want to find that, let's see, our friction, let's see, I called it friction 1 and friction 2. For friction 1, okay, we've got, no, not friction, I'm sorry, tension. We're looking at tension. Okay, so we've got tension A and tension B. Okay? So how would we find tension A and tension B? Well, we can look at the summation of forces, right? Tension A would equal M1A minus mu K M1G. We have all of those numbers, right? M1 is 2, A is 0.309. Then you've got minus 0.36 times 2 times 9.81. Okay, so tension A, get rid of you. Tension A equals approximately 7.6 newtons. Okay? Then we'll do the same for tension B. Ooh, that's a doozy. You've got M2A minus M2G sine theta minus mu K M2G cosine theta. So when you put your values in and put that in your calculator, you should get approximately 9.22 newtons. So that's how you can find the tensions in those. That's by going back over here and looking, where is that tension A? Whoops, where is that tension A and tension B? Solve for that, solve for that. Now that you have acceleration, you've got all the numbers you need. Right? Now, question C asks our final question. Why does the pulley cause the tensions to be equal, or sorry, to be unequal? So the reason that is, right, because the whole point of this was that real pulleys are affecting our tension. That is because tension B, right, is not just pulling M1, okay? It's pulling M1 and it's having to turn this pulley that we're now recognizing has mass, whereas tension A is just pulling M1 and that's it, right? And now there's the friction, right? So there is, it's not just sliding across a frictionless surface, but tension B is pulling M1 on that friction surface and it's rotating the pulley, which now with moment of inertia we know takes some effort. Right? All right, so that is our video on pulleys, and we will continue with chapter 10 in our next video.